We are quick turnaround people. But nothing about research is quick. Research is a really slow, methodical, diligent pursuit of the truth, the first point. So again, you're swimming counter to the current of your culture, and that'll cause some pain over time. Be dedicated to the truth thing, and you'll be able to put up with the news cycle thing, or the quickness of life. And the third point I'm aware of is, a therapist told me, our society is now selecting for and promoting the production of extroverts rather than introverts. For any of you who've ever done it, research is a pretty introverted deal. You might end up in the bar on Thursday or Friday or Tuesday or all of them, but in the end, it's you and your research project. It's a pretty introverted deal. And we're not creating most of those, and we're not stroking a lot of introverts anymore. So don't feel bad if you don't feel like you're just like everybody else, because maybe you are on a little bit different path, but that doesn't mean stop. That means just understand. And I couldn't help pulling on something to honor Dr. King today. He said this. This is one of the most profound things he said many profound things, but this is incredibly profound to me. The arc of the moral universe is long, but it bends generally toward justice. And I thought that was such a vivid picture for me. And kind of what I'm saying to the students is that the arc of the valuation of fact and truth can be long, but in the end, I think it'll win out. And that's what this session's all about, and that's what I encourage them to go for in their careers. Okay, let's get started. First speaker today is Jessy Mayer. Jessy is from Marysville, Washington, originally a suburb of Seattle. His BS degree is in biology from Washington State University. He's currently a PhD student at the University of Nevada, and he expects to graduate in about the summer of this year. His professional interests are molecular biology, synthetic biology, genetics, and biofuels. His personal interests, backpacking, hiking, biking, and pretty much up in the Sierras, like above 5,000 feet maybe. Just like with us, you ask him what he wants to do when he grows up, and he'll say he's not sure. Some days industry, some days academia, but it changes pretty regularly. So Jessy, welcome to the podium. Let's hear what your talk's about.
All right, thanks Mike for the introduction. Today I'm going to talk to you about a couple strategies that our lab is doing to try to produce crops, and in particular bioenergy crops, for hotter, drier regions of the world. So I got to kind of cover my PhD life story in about 10 minutes, so it's going to be a little fast, but I do want to make sure I explain everything really well so you guys can understand what's going on. So first of all, we don't need to wait for climate change to give us dry land. 40% of the global land area is already arid or semi-arid. You can see that Nevada is part of that wonderful arid region. There's also lots of other parts of the world. And this land area can't produce crops. I don't have to tell anyone in the room because of water issues predominantly. If you try to throw soybean in the desert, it's going to dry out. But what a lot of people don't understand is the reason why they dry out so quickly. It's not because the plants are using that water for growth and running out of it. It's because of a process called transpiration. So transpiration is the loss of water through the stomata, or the pores that you find on the leaf of the plant. Now you do need this to some extent. It's what drives water and nutrients from coming up out of the soil and into something as high as a giant tree. But when you put a crop in the desert, this really gets out of hand. It gets to the point that 97 to 99.5% of the water that plant is taking up is just going straight out of those pores. So there are plants that grow in the desert, and most of them are able to do this through a process called crassulacean acid metabolism, or CAM. So don't get hung up on this figure too much. What I want to show you and point out in it is that those stomata or pores are opened at night when it's cool out in the desert. They then take the CO2 in and turn it into this 4-carbon acid that gets accumulated in large quantities so that during the day they can shut those pores entirely, perform photosynthesis from that C4 acid and not have the water loss through the stomata. So because of this system, they have greatly reduced water use. So C3 on this graph is most traditional crops, your rice, your wheat, your soybean. C4 photosynthesis is corn and sorghum and a few other crops you might know. And then there's CAM on the bottom. This is water use normalized to biomass. And you can see that even the most water use efficient traditional crops use more water than the least efficient CAM plants. On average, they use about 1/6 the water for the same amount of biomass. And so this is something our lab is really excited about. And we have two different types of strategies to try to utilize this CAM to grow better arid and semi-arid crops. The first is CAM biodesign, which is to try to identify what makes this CAM photosynthesis happen. What are the enzymes, what are the genes that we need for it, and can we develop these into major agricultural crops that we already use? The other project called oleogenic opuntia is a prickly pear cactus, is going the other direction. Can we take something that's already prolific in the desert that grows really well under low water conditions, and can we make it more agronomically relevant by increasing oil content in this case? So I'm going to go over the two of these real quick here, because I could spend an hour talking about this CAM biodesign project on its own. But basically what we're doing is it's a 3-step process. So we started by sequencing the genomes of a lot of different CAM species, looking at what do they have in common, what are the genes, trying to single out what are those genes that are letting them do this really water efficient photosynthesis. The next step is CAM building, where we started taking one or combinations of those genes and the regulators that control them, and then deploying those into plants that we can work with. So the little thing on the top right there is Arabidopsis. It's the mouse of the plant world in the sense that it's cheap, it's quick to grow, it's easy to work with. So we try things out there, and then when they work, we can deploy them into bigger crops. The one on the bottom right is poplar. This is a DOE-funded project. They're really interested in poplar, so that's one of the first crops that we're starting with. So we try things out, they don't always work, or they work not quite the way we want to, so then we go back to the drawing board, add another gene, change things up, and then just kind of keep repeating that process until we get some interesting results. And we have had some interesting results with some of the genes. One that I wanted to point out in particular is for succulents. So succulents is what makes the leaves of most CAM crops pretty thick. You can think like aloe vera or cactus having those thick leaves. It's what allows them to store that CO2 at night. And so we found a succulents gene. This one was actually in grape berries. It's what makes the fruit thick and water rich. And we put this into our Arabidopsis crop. And what we got were some really big plants. So the one on the top here is going to be what it would normally look like. And this one on the bottom is when we added this succulents gene. We got 3 times greater biomass in the leaf tissues, but we also saw a greater seed yield. What was really interesting that we didn't expect at all was also a very strong salt tolerance. Our theory behind this is we've made these leaves succulent so they have more room to kind of disperse the salt and not be as greatly affected by it. So this is pretty telling. These are grown in half molar salt or sodium chloride. That's basically ocean water. And the plants on the left are your traditional Arabidopsis plants. They're pretty dead. The ones on the right have this succulents gene. They're not 100% healthy, but they're growing and doing a lot better than most anything on a similar kind of situation. So this doesn't mean a lot yet because it is in this Arabidopsis, this model plant, but we have put it into rice where those are growing out and the results are looking pretty promising. We have a patent application on this because we do think that there's a lot of agricultural potential just in this succulents gene. So coming back to cactus, that was in my beginning slide there. This is the second aspect of what we're doing and more the focus of my dissertation specifically. The reason we picked out this prickly pear cactus is that it's very much above ground biomass, so it's pretty easy to harvest. It's easy to propagate. You can do it clonally by snapping a pad off and putting it in the ground. It produces another plant. Very drought tolerant because of this CAM. And in Mexico has been used for a while as a food and forage crop for the fruit and the tender pads, so there was some data available. And then Of course, it's got a lot of biomass production compared to some other desert crops. So the reason why we're not producing biofuels out of it now is that it's got a fairly low sugar and oil content. So I talked a little bit more about this at the biodiesel technical workshop, but I wanted to make the point that oil, we traditionally think of oil coming from seeds because commercial scale oils are extracted from seeds, but the vast majority of the biomass is non-seed tissue. And it's not that there's not being oil produced in these non-seed tissues, it's that it's regulated differently. It's the same oil that you'd find in seeds, but in seeds, oil production is very rapid and oil breakdown is pretty slow because the plant wants to accumulate oil there to use it as a resource when it's time to grow, to germinate that seed. In leaves, same oil is being produced, but just very slowly, and then if there's too much oil, it's degraded very rapidly because the plant thinks that there's a better place for that energy to be. So we and other groups have asked the question, well, can you modify plants to produce oil in leaf tissues as opposed to seeds to have a greater amount of oil available? Going back to one of these model plants again, this is tobacco in this case, you can see these plants, besides the fact that they decided to take their pretty pictures after they had sampled, bad idea, they look pretty healthy, the wild being on the left, the transgenic on the right. The difference is those transgenic plants had 100-fold greater oil in the leaves, to the point that the average oil content was 12% by dry weight. Soybean, by comparison, is 20% by dry weight, but you have a lot more leaf biomass. So this was really intriguing. What was also interesting is because they used seed oil regulators in the leaf tissue, it actually changed the oil profile away from predominantly 18,3 fatty acids and more towards 18,1, 18,2, which is what we wanted to see. So we thought we could use this strategy to increase the oil content in our prickly pear cactus. So the summary, real quick, of this project, which is called oleogenic opuntia, or sometimes desert diesel, is to identify these same genes that we saw in tobacco in our prickly pear cactus that increase oil, that protect oil, prevent it from being broken down, use transformation to try to insert these. It'd be over the scope of a PhD to try to do breeding because it takes a few years to get seed, and then screen these pads for increases in oil content. So we're working on that actively to try to get this transformation process to work. It hadn't been done in cactus previously, but we have been able to transform a couple cells at a time, and so this is always my test of how crappy a projector is in a room or how much light there is, but what's important is we're using a green oil stain, so the more green that you see in a picture, the more oil bodies are there, the more oil that there is to extract. So we have regular cactus on the left, and then kind of in this square on the right is our transgenic. It's looking to be about a 10, 15-fold increase in oil production, not what we would need to be economically viable, but we're working on it, we're refining it as we speak. Okay, so to wrap things up, I just wanted to introduce you guys to this CAM photosynthesis, this highly efficient photosynthesis that allows plants in the desert to use considerably less water, that we've identified genes responsible for this CAM photosynthesis, and we're testing them right now in model species, but also with the hope of getting those into major crops. Approaches to increase oil in vegetative tissues have been successful, and now we're trying to put that in a drier crop with opuntia. And just taken together, we think that both of these strategies in different ways have the potential to get us to a low input yet agronomically relevant crop. So with that, I wanted to thank a lot of people in the lab that have helped me with this project. And then our funding, the oleogenic opuntia project, is being funded by an EPA fellowship I received. And then, as I said earlier, the CAM Biodesign project is under a DOE grant. So with that, thanks for listening, and I'm happy to take any questions.
Thank you, Jesse. We have time for questions if there are any. Yes, ma'am.
Do you get opposition for using biotech? And if so, what is your response to the people that say that you shouldn't do it?
Yeah, that's kind of one of those hot topics in the public domain. It's kind of interesting. Our greenhouse facility has these 12-foot fences around it because we've had people try to burn it down because we work with these kind of transgenic crops. And it's something that we as a field have to kind of advocate and educate about, because the USDA has supported it in the sense that if you go through the regulatory process, you can get these out in the field. But what we've found is the people who want to grow it, the farmers, are very open and supportive about it. It's typically the people that have the most opposition are not the people that we're focusing on with this kind of stuff. So, yeah, I think we just need to educate people more than anything. Yeah.
Do you know if the regulatory process is different if a crop is just meant for fuel instead of food?
Can you repeat it, Jessy?
Yeah, so the question was if the regulatory process is different for approving a GMO if it's a food crop versus a fuel crop. Unfortunately, it's not, because one of the big things that they're looking at is, are your genes going to cross into native species and get out there? That's going to happen regardless of if it's a food or a fuel crop. That said, one of the strategies that we're trying to approach is called cisgenics. I was talking to Mike about this at my poster yesterday. The idea being that if you use the original Opuntia genes, because like I said, those oil synthesis genes are there, but you change the way they're regulated to increase how much of that enzyme that's converting the oil is present. If you rearrange the existing genes in the cactus, you can get away from this regulatory hurdle because you're not bringing foreign DNA into the plant. So that's been the plant biotech community as a whole has been adopting this process, and it's gaining traction. So we may go that way to try to get away from some of the regulatory hurdles. All right, thanks.
Thank you, Jessy. The speakers will be available after this session. If you should have more questions, just come on up. Our next presenter is Rachel DeMyers. Rachel is originally from Aurora, Illinois, but was raised in Wichita, Kansas. She's currently at Kansas State University, where she's pursuing a bachelor's degree in chemical engineering with a minor in chemistry. She's co-founder of the BioDiesel initiative at Kansas State, which collects used cooking oil from around the campus and converts it into biodiesel. She's expanded that work recently, studying the production of soap from the glycerin byproduct, as well as learning, refining, and developing testing methods to monitor the residual metal levels in the biodiesel that they produce. Rachel?
Good morning, everybody. Here, I'm going to start a timer so I kind of know where I am on time. All right. So like Mike said, my name is Rachel DeMyers, and I'm the co-founder of the BioDiesel initiative at Kansas State University. This year, my research assistant, Katie Worm, and I began testing residual metals in our biodiesel product that we produce at Kansas State using flame atomic absorption to determine if the biodiesel meets the ASTM standards, to find a minimum number of washes that are required to meet those standards, and ultimately to determine whether or not our biodiesel is safe to use in trucks. So today I'm going to talk to you about why we wash our biodiesel and how we do so, what flame atomic absorption is and how it works, and then the results that we got with flame atomic absorption. We test 4 metals: calcium, magnesium, potassium, and sodium. The problems that we encountered while collecting data, and then how we approached resolving those issues, the conclusions that we came to, and then I'll give some acknowledgments and questions. So we wash our biodiesel first by, so we want to remove the sodium catalyst that we use for the triglyceride conversion, as well as any residual cations that might be in our feedstock. We do this by adding water onto the top of our finished biodiesel product, which is more dense than the biodiesel. So it sinks down to the bottom, and with it takes those cations that we're trying to get rid of, and then we drain off our water. So atomic absorption is the absorption of ultraviolet or visible radiation by free atoms in the gas phase. Flame atomic absorption works by drawing the liquid sample, which we dilute our samples in ethanol. And so that solution goes into the nebulizer using acetylene and compressed air to produce free atoms. The nebulizer is required because the sample needs to be vaporized in a flame in order to be converted into atoms that absorb. The free atoms absorb light from the halocathode tube, which ascend from the ground state to a higher energy level. Various different kinds of lamps are used based on the specific metal that we're looking for. So you can't run multiple metals at once. We have one separate for calcium, magnesium, potassium, and sodium. These lamps emit discrete wavelengths, which are absorbed by the atoms. The monochromator isolates the absorption line from the background light due to interfaces, and then the detector reads those results, and we're able to find the concentration based on absorption. I didn't mean to do that. The Beer-Lambert law provides the basis for calculating these results using absorption. The amount of absorption is dependent on the number of atoms from in the ground state and the path length of the flame, as well as the absorbency of the ground state atoms. Okay, there we go. So according to the ASTM for B100, calcium and magnesium have to sum to be less than 5 milligrams per liter of biodiesel. We found that the amount of calcium and magnesium decreases for our biodiesel in a fairly linear pattern. The average amount of calcium in our biodiesel is pretty small. It's a 0.053 we found. So that's just on 4 samples. So we're gonna obviously be taking more samples as time goes on. And the average amount of magnesium was about 0 milligrams per liter. The sum of these two cations is significantly less than 5, so that's really good. So the potassium and sodium in our biodiesel has to, again, sum to be less than 5 milligrams per liter. The sodium amount for the metal removed is significant in the first wash, as you can see that big dip, and then the potassium decreases in a fairly linear pattern again. The average amount of potassium in our biodiesel is 0.008 and sodium 0.01. So once again, summing less than 5. So we encountered a few issues while collecting data. The first being that our nebulizer was getting clogged, and that would cause extreme irregularities in the data that we were collecting. So to reduce this from happening, what we did was we cleaned the nebulizer using water, ethanol, and nitric acid solution before we used the machine, after, and in between each sample. The second issue we had was getting negative absorbance values. So basically we just accounted for this by making the blank 0 and adjusting all values following accordingly. We discovered some important information to make our data more consistent and reliable. The first was that at higher concentrations, the absorbance is less consistent. We believe this was probably because of the formation of oxides more readily at higher concentrations of metals. When oxides form, there is there is not much more metal to absorb light in the flame AA, making the absorbance lower than it should be, and therefore more dilute solutions yield more consistent results. The second issue that we resolved was the variation absorbance giving flow rate. More oxides will form if the flame is cooling. We believe that as the ethanol content in the flame increases at high flow rates, the flame will cool off and more oxides are going to form, and thus we came to the conclusion that slower flow rates yielded better results, and as well as cleaning the nebulizer frequently helped keep the flow rate more consistent. In conclusion, we recommended that there was 2 washes for the biodiesel that we make to remove all the cations that are of interest, and 3 if the reaction needs to be pushed or if there's an emulsification. When I say pushed, I mean that a reaction didn't go to completion due to high free fatty acid content or something like that, and so more additional catalysts needed to be added to complete the reaction. And emulsion is the combination of water, biodiesel, soap, sometimes glycerin, and unreacted oil, none of which are actually chemically bound. And we break up our emulsifications by adding hot salt water to the mixture Although this method is great to break up our emulsions, there is residual sodium that stays in the biodiesel, and so that's the reason we need an additional wash. We discovered that for the best results for our testing using atomic absorption, the flow rate should be lowered, and the standard concentrations that we use to create our calibration curve should be no more than 1 part per million. Going forward, we're going to measure the cation values of our feedstock and compare those to the stages after washing so we can get more accurate results. So I'd like to also say thank you to some people that made this research possible. First, I'd like to say thank you to my assistant, Katie Worm. She's been really enthusiastic and has a great desire to learn and expand the project further. I'd like to say thank you to Dan Higgins. He wasn't able to be here, but he's the advisor for the project, and he's been really helpful kind of with helping us to interpret the results that we get and understanding them. I'd like to say thank you to Ed Brokish. He is here. He's the advisor for the BioDiesel initiative at Kansas State, and he's been extremely helpful. And lastly, I'd like to say thank you to the Kansas Soybean Commission for providing us with funding and for support. All right, and now any questions?
We have time for 1 or 2 if anybody has any. Yes, sir.
Actually,
Could you repeat the question?
so the question was if we've considered dry washing. So we have another student here, Devin, and he's actually going to be investigating that this next semester. So we kind of just picked using water because it's the cheapest right now. Our project's actually only 5 years old, so we will be investigating that, yes. Any other questions?
Very good.
Awesome, thank you.
Rachel will be available. Thank you. Stanley Anderson II is our next speaker. Stanley is a native of Paterson, New Jersey originally. Currently he's at Clemson, where he's a master's student in the grad program in biosystems engineering. He's had a long interest in renewable energy systems. His current research, as you will see, is on the production of biodiesel by enzymatic catalysis. Down the road and into the future, he would like to stay involved with renewable fuels, further studies on enzymatic catalysis, as well as other methods of creating a more versatile biodiesel for different custom niches, perhaps. Stanley?
Good morning, everyone. Again, my name is Stanley Terrell Anderson II, and my advisor is Dr. Terry Walker. And I'll be presenting a yield analysis of enzymatic interesterification using cottonseed oil. So a brief background is, first I would just like to start off by saying that our sponsors for this project is the Cotton Board, and they're continuing to support research initiatives that forward the advance of cotton as a product. And in my background information, we'll only be discussing the first phase of the research, which is sample generation, and it's going to overview the feedstock, the purpose of the enzyme, the particular reaction, and some products, before I discuss the methodology and initial results, before we get into questions. So in general, esterification of biodiesel works in a more traditional route as shown in image labeled 2. And that's via using methanol and adding that with your triglyceride. You can use any type of catalyst that you want, whether it's enzymes or metals or chemical catalysts. But the reaction that we'll be discussing today is listed in image 3, and that's when you replace the methanol with methyl acetate to get your methyl ester. I know it says tributylene, but you can in general use any triglyceride, but you can get your methyl ester as well as a byproduct known as triacetate. And that product has been noted to improve the cold flow of biodiesel so that it can operate at around freezing temperatures more readily. and it allows the organic fuel to be operated in different climates. And we chose cottonseed oil as our feedstock of choice because that also has a pigment in it called gossypol. It's a natural antioxidant. It also improves the life of the plant by making it more resistant to insects. But it's a natural antioxidant, and it has been noted to improve the oxidative stability of the fuel to greater numbers that exceed ASTM standards. So again, a brief overview of the two processes. So insert esterification uses an alkyl acetate. Doesn't have to be methyl acetate. It can be ethyl or propyl acetate. And its byproduct is triacetin. Some of the drawbacks that have been observed are that higher molar ratios have been required to push the reaction forward, as seen in studies done by Casas. And it's slower overall as a reaction. And it's also much more prone to moving backwards. So more has to be done to push that reaction forward. Transit esterification is done using an alkyl alcohol, but the byproduct is glycerol, which is not soluble in biodiesel, and it can be used as a fuel additive, while triacetin is soluble and it can be used as a fuel additive. And enzymatic production is denatured by alcohol, so it often has to be done in more process-consuming steps, and there are separation issues that occur as a result. So some of the benefits of triacetin are seen here. Those graphs may be pretty hard to see, but the main thing is that there are drawbacks to when you increase triacetin. One of those is that the energetic density goes down. Triacetin is a much smaller molecule, so when you burn it, it produces a lot less energy. But typically at around 10%, you can still meet most of ASTM standards with various different oils. A lot of properties change depending on what oil you use as the feedstock, but at around 10%, you can still meet a lot of the ASTM standards for like cetane number, as well as energetic density and the flash point of biodiesel. So the big questions that we had going forward was that what are the best conditions for reaction? How well does this fuel perform? And what post-reaction methods would get the best fuel properties? So the first question is definitely going to be answered today, or well, some of them are, but the other two are likely going to be for future studies, but these are the big questions that we went in before our investigation. And in phase one, we were focused on generating our samples and confirming that what we were getting was actually biodiesel. The current acyl acceptor molar ratio for the methyl acetate was 12. The enzyme weight varied between 3, 4, and 5% for the crude cottonseed oil, and 4 and 8% for any glandless cottonseed oil. But that will be discussed when I discuss the conjugated lipase that was done in comparison. So water weight was varied at 3, 4, and 6%. And the temperatures that were used were 35, 40, 45, 50, and 55 degrees Celsius for conjugated lipase, and 35 for the crude cottonseed oil, which used traditional Versa. And in the process of investigating this project, I was given the opportunity to test conjugated Versa, which it works by absorbing the enzyme to a product, and it was done to increase the temperature stability, and those results will also be represented in the post-analysis. So some of the analytical pitfalls that we did encounter is that we had a lot of inoperable equipment, so we weren't able to test as many results as we would like, and we also had a lack of methods, whether it was from gas chromatography or high-performance liquid chromatography, that just weren't able to handle cottonseed and gossypol. One of the problems with gossypol is that it has a boiling point of, I believe, 590 C. So putting that through the GHC was very risky, and it was something that we opted not to do until the last minute, just to see if we could get anything. And since there were few prior experiences with this fuel, we just had an overall difficult time of figuring out what was the best way to test this. And so we used qualitative approaches just to simply confirm, was this reacting and what steps do we think we need to attack to improve fuel quality overall. And so again, I think I mentioned this before, but data represented was the ones that we have currently made. We have 12 triplicates of the heavy pigment cottonseed oil, the crude dark oil, and the glandless cottonseed oil, the one that doesn't have any gossypol in it. It was selectively bred to not produce this pigment. We have 15 single samples, and you can see the variables that were varied as a result. And so some of the qualitative inferences that we use the 27.3 test to essentially validate any chromatograms that we got. The chromatograms that we did test, they had a propensity to give broad peaks. These peaks weren't considered to be research grade, and we found out later that that was due to imperfections in the column. We clean the column before every run, we get better peaks, but I'm still not comfortable integrating those areas at this time. So we analyze those graphically just to see, relatively speaking, is anything happening? And as you can see from this 27.3 test, which is often used for just determining glycerol, since you're adding methanol, that's also going to cause any unreacted oil to drop out. And as you can see, our oil is primarily triglycerides. So we weren't able to produce anything. And this is one of the samples that we use, and it shows some of the problems with the broad peaks towards the end. The 7.5 to 10 minute region is where standards have been observed for fatty acid methyl esters, but towards the end, you get a plethora of triglycerides. So relatively speaking, we can see that we're getting more on the triglyceride end than the ester end. So we currently are not toting a very, very strong reaction. This was representing one of the better crude cottonseed oil samples, and this one is representing a transesterification of glandless cottonseed oil, and this one was also done as comparison to see if the issue was the enzyme or whether this was just something that was occurring because we were using intersterification instead. So some of the areas we have been able to identify for attack. In general, we observed a better result with the conjugated lipase, and that's something that we would probably like to use going forward. Overall, higher temperatures produce better results, and that makes sense because of better thermodynamics. And again, transesterification, as hypothesized or noted in literature, it produced a much greater effect. One of the things that we plan on doing is increasing the acyl ratio, as that may not have been high enough based on a lot of kinetic studies on there. And we don't believe at this time that water content was an inhibitor, as we expected that to. So we are going to continue with using the same ratios for that. And it also may be that our reactor configuration isn't producing good mixing. So to the right, that image is just showing how we conducted our trials. We just put a beaker inside of an incubator and had that spin triplicate samples overnight. And that process may need some improvement as well to get better mixing. So again, we're going to reset all the apparatus, increase the speeds from 250 RPM to maybe 300 to see if we can get better mixing, and vary the enzyme loading a little bit more to be more representative of what has been seen in literature. Some have used low weight enzymes, but some have used higher weights. So we may expand our range a little bit more to see if we can get something, see if we can push a reaction. And again, increasing the acyl acceptor ratio, as some have been seen as going as high as 60-1, and our current capacity has only been using 12-1. So we'll be trying a lot more different techniques to try to tune the results to get a better reaction. Here are a few of the references that we used, and are there any questions?
Any questions for Stanley?
Don't be shy.
Suppose you're,
Go
I'm
ahead.
sorry, yes, sir.
So you have like high concentration of your acyl ratio in your starting material, right? Have you
No, we haven't. The only acyl ratio that we tried is 12 so far, and we've observed that that isn't producing a reaction. Again, it could be a wide variety of things. I know we were manipulating a lot of variables, and the plan is to do this in a factorial format to determine which one is the most influential. But the only one we tried so far is 12, but we've noted that in literature, a lot of the ones that were able to produce higher yields, they use higher ratios.
Further questions? I've done reactions kind of similar to that, and with regard to the mixing, I'd point a finger at that. I've run them in small, totally filled tubes, a small enough tube to be totally full, and then put them on a radial mixer and invert them, so there was enzyme mixing through the liquid all the time. You have a solid and a liquid, and you need to ensure constant contact, so maybe that's something to look at as well.
Yeah, thank you.
Thank you, Stanley.
Appreciate that.
Yeah. I think this is about the most international student panel I've ever been at. Our next speaker is originally from Bangalore, India. Bring up his talk. Dr. Vinayak Pachapur received his PhD last week. In Quebec, Canada, from the in process engineering from the Institut National de la Recherche Scientifique. Thank you very much. His PhD thesis work, as he will describe today, was on the production of biohydrogen from the crude glycerol byproduct of biodiesel production. He's interested in expanding this research and is interested in a career in biofuels and bioenergy if at all possible. So Dr. Pachapur, please.
Good morning. Thank you. Good morning, everyone, and thank you, Mike, for the introduction. So as you can see, my title goes with the using of crude glycerol into value-added product. So our sponsors were the CRIC. So they wanted to convert this biodiesel waste into some value-added products. So what we had option was to go for a economical process where we can use this crude glycerol. So I choose to produce biohydrogen. So as you can see, why hydrogen? So hydrogen is considered as a clean fuel, as it has the only byproduct is water, and it has a high energy content, which is almost 3 times to that of diesel fuels. But the current commercial scale production of hydrogen involves use of natural gas, oil, and coal. So most of the production of hydrogen is for energy intense, and they are more expensive. So it goes with the operating cost of 80%, and it works at a temperature of 700 to 1000 degrees Celsius. And in the end, it releases CO2, which is a greenhouse gas. So researchers are looking for the alternative production of hydrogen. So one alternative is the use to produce biohydrogen, which is environmentally friendly and less energy demanding. So we can produce biohydrogen at a condition less than 36 degrees Celsius. And in the end, we can produce 99.99% purity. So it can be produced from various substrates. As you can see, it can be produced from monosaccharides, polysaccharides, and organic acids. So the recent trend for biohydrogen production is utilizing the organic waste because they are inexpensive and abundant raw materials. So one such abundant raw materials is crude glycerol. As you can see, it is produced along with that of biodiesel. So for every 100 kg of biodiesel produced, we produce around 10 kg of crude glycerol through transesterification process using different generation feedstock in the presence of methanol. So here the biodiesel is considered as an alternative and renewable fuel, and it is also blended with petroleum fuel. So the demand for biodiesel is increasing, and along with that, you can see even the production of crude glycerol is also increasing. So this is the estimated production of biodiesel across different continents. So as you can see, Europe are the first, and followed by the Central and South America, followed by Asia and others. So the estimated biodiesel production by 2020 will be around 150 billion liters. So along with this, there will be also production of crude glycerol. As you can see, there is the estimation for crude glycerol also. Here I have estimated value of crude glycerol for 2012 for Canada, that is around 19 million liters. So researchers are exploiting for the sustainable management of crude glycerol, because small scale and large scale industries are facing problems with the glycerol management. So what are the management of the crude glycerol? So as you can see, the crude glycerol varies from, the composition of glycerol in the crude glycerol varies from 23 to 70%, and it also contains various salts, methanol, and even the material organic non-glycerol also, ranging from 3 to 6%. So if we consider for an environmental release, then we need to pre-treat this, and there will be additional pre-treatment cost. And in case if we don't pre-treat and we just release it into the environment, and it will cause a toxic odor release, which will be dangerous for the living ecosystem. And in case if we consider for a combustion and landfilling, and priority is that we need to determine the waste, and which includes the additional cost. And in case of landfilling, there are some cases where because of the fill drain runoff, it has caused a problem for the ecosystem. And in case if we are considering for a bioconversion of crude glycerol into 1,3-propanediol and ethanol, then we need to input more of media cost for production of these chemicals, and even at the end, due to the impurities presence in the crude glycerol, there will be more downstream processing cost involved for recovering of these particular chemicals. So what is the, so for, as you can see, for the every decrease in 0.2 price, 0.22 per kg of crude glycerol, there is an increase in the production cost of biodiesel. So there must be some alternative ways to utilize this crude glycerol. So what we did was we looked into some of the different methods. Then we were shortlisted to two of the methods wherein we use the glycerol purification to produce glycerin, and in the other approach we selected dark fermentation to produce hydrogen. So in both the cases we calculate the energy input for conversion of 1 kg of crude glycerol into either hydrogen or into the glycerin. So we selected these two methods, and we determined the energy input across each of the steps. So here I have the total energy input for the dark fermentation, that is to produce biohydrogen. As you can see, there are different steps involved in the dark fermentation. That is inoculum step, media preparation step, sterilization, incubation, and fermentation step. So each of the steps we determine how much energy input will be, and we calculated the total energy input for the dark fermentation to convert 1 kg of crude glycerol into hydrogen production. So it was around 179.45 millijoules. So in the similar way, we calculated the same energy input for that of glycerin method for purification of glycerol. So we ended up with the total energy input for glycerin purification was around 873. That was around 4 to 5 times in comparison to that of dark fermentation, as you can see here. And even we consider the end product, that is hydrogen, which has a market value of around $3 per liter. This was in replacement to that of the biodiesel, diesel fuels. So, and if we consider that of the glycerol, pure glycerol, it has a market value of 0.66 per dollar. So as we can see here from these results, we shortlisted the dark fermentation, that is the bioconversion of crude glycerol to hydrogen was an energy efficient option. So we shortlisted crude glycerol and even the dark fermentation process for hydrogen production. So what are the other problems involved during the hydrogen production? So first problem is that of the substrate inhibition, because presence of glycerol in the crude glycerol acts as a inhibition for the microorganism. So what we proposed was we used the apple industry waste, that is apple pomace, and we hydrolyzed and we used it as a co-substrate to take out the problem for the substrate inhibition. In another problem, we have the viability of glycerol. So here we use the surfactant, that is twin 80, to solubilize the glycerol and make it more available for the microorganism to utilize. And in the other case, if we want to produce more hydrogen, there is an involvement of cost because we need to maintain the buffer, and even we need to go for some of the costly immobilization steps. So here we propose to use another industry waste, that is eggshell, so which has around percentage of 97% of calcium carbonate, so which can be explored as a neutralizing agent, and it can even act as a immobilizing agent for the microorganism to attach and produce more hydrogen. And in the end, whatever the spent media is produced from the dark fermentation, so we wanted to utilize in the one or the other way. So we proposed to use mixed and photo fermentation, where we use the spent media as a replacement for the commercial media for in case of algae production as a lipid. So this basically explains how the process goes. So when we have the crude glycerol from the biodiesel industry, then with the help of two of the best high-producing microorganisms, that is Enterobacter aerogenus and Clostridium bitricum, these two were used in a co-culture system. They helped in each other to produce more hydrogen. So this was a novel approach of using two organisms in the presence of crude glycerol to produce hydrogen. And in case if some of the media components which were costly, so we tend to replace with some of the other industrial waste. So we use eggshells and even the apple pomace. So here you can see that apple pomace was used as a co-substrate for these two organisms to produce hydrogen, and eggshell was used as a neutralizing agent to produce hydrogen, and it also acted as an immobilizing agent. So here you can see both the organism, that is Enterobacter aerogenus and Clostridium, they had the same kind of pathway for conversion of crude glycerol into hydrogen. They followed both oxidative and reductive pathway. So in case if the biodiesel industries are going for some other value-added product, so if by using crude glycerol and just water, they can even produce acetate and ethanol. And in case if they add the media component, they can even produce the butyric acid. And in further media components, they can even produce ethanol and 1,3-propanediol. And if in case of some of the buffers, they can even produce ethanol and 1,3-propanediol. So the use of conversion of crude glycerol by dark fermentation not only helps in producing hydrogen, but also producing some of the value-added products. But the best part of producing hydrogen is that as it is a gas, it is get collected into the headspace. So you don't need to have a further downstream processing to purify this hydrogen from the media component. So that is why we selected hydrogen as our main product. So here in my last paper, we also proposed an efficient closed system for a biodiesel industry. As you can see, when the biodiesel industry uses the generation feedstock through the transesterification process to produce biodiesel, and whatever the byproduct is, crude glycerol, this can be divided into two parts, and one part can be used as a co-culture in a semi-continuous, so for a 100-liter working volume, we can produce hydrogen. And whatever the spent media is produced from this can be divided further to use mixed culture for hydrogen production and also for the photofermentation for lipid production. So the other part of crude glycerol can be used as a substrate for the mixed culture to produce hydrogen. So here the mixed culture, even whatever the waste treatment plant the biodiesel industries are taking out, whatever the secondary sludge is produced, this secondary sludge can be used as a seed inoculum for the mixed culture, and accordingly it will help in producing the hydrogen. So even in case of photofermentation, whatever the spent media we have used, so this can be used to produce lipid, which with the best results which we had across the studies was 21.25 kg per meter cube per day. So whatever lipids are produced, this can be used as a generation feedstock again. So here we have a complete closed system proposed for a biodiesel industry. So in the media preparation cost, as you can see, we were able to bring down the media preparation cost from $43.95 to around $3.15 by using just whatever industrial waste we had. We replaced some of the commercial products which were higher costly. And here in the results and conclusion, this sums up my PhD project where I use different strategies to increase hydrogen production. And what I can propose is, with the help of bioconversion of crude glycerol to hydrogen, this will be a good proposal for a biodiesel industry where the produced hydrogen they can use as a energy, electricity, and heat. So in the end, we are looking for more of hydrogen stations, and even in some countries, they are even using the biohydrogen produced as a fuel cell for some of the cars. Thank you.
Questions? There's certainly a lot of detail on the later slides. If anyone would like to go over it in more detail, I'm sure Dr. Pachapur will be available. Thank you very much, and
Thank
good
you.
luck in your career.
Thank you.
Our next speaker, Musa Salihu Danlami, may take the prize for longest distance traveled, in that he is from the United Kingdom. Originally a native of Nigeria, his early training was conducted in Nigeria. He has a BS degree in chemical engineering and a master's in environmental engineering, and he is presently at Newcastle University in Newcastle upon the Tyne in the United Kingdom, where he expects to receive a PhD in 2019 on the work that he is studying today. Prior to his doctoral program in Nigeria, he was and continues to be a lecturer in materials science engineering, and he was also with the National Environmental Standards and Regulations Agency of Nigeria, where he was a regulation officer in charge of the chemical industries in Kano in 2010. Thank you for coming this far. We look forward to your talk.
All right, thank you, Mike. It's a pleasure being here. Thank you, everyone, for listening this morning. What I'm about to present is like a brief summary of the preliminary results of my PhD, which is exactly a year old now. And it's titled Cost-Effective Biodiesel Production from Microalgae by Oil Extraction in a Foam Column. Basically, this is a kind of intensified separation process looking at achieving three different objectives, one of which is solid liquid separation. The other one is cell disruption of the algae, and the last is oil extraction as stated in the title. So, this chart is according to BP report of energy in 2016. It shows that only 13% of total energy consumed in 2015 came from renewables that are not, basically non-fossil fuel, which means that about 87% of energy consumed in 2015 is still from the fossil fuels. But is there a problem with that? Well, for those of us who are advocates for environmental protection and safety and all that, would say that's a problem. So what do we do about it? Because those are the challenges, a very few of them, which I believe most of us are aware of. The fossil fuel is facing security challenges in terms of supply. And of course, it has the big issue, which is the climate change issue. And there's this argument as to whether or not, fossil fuels are exhaustible. Well, if they are or they're not, it doesn't change the fact that they are non-renewable. And of course, they are a major source of CO2 and other greenhouse gases. and that makes them a threat to human and environmental health. So, why algae? Well, it says there that it's a third generation biofuel, but this is not like trying to bring down the other feedstock, especially here in the US, Sussex story so far with soybean, but it's just a way of pointing out some of the advantages that are associated with algae biofuel, which most of us are aware of. And another advantage is higher photosynthetic efficiency compared to terrestrial plants. It also has rapid growth rate as well as high lipid accumulation per body weight. Now, with all of that advantages, it also comes with serious disadvantages, or call them challenges if you like. Now, to produce, anyway, all of this is around the fact that they are so dilute in nature. Usually, when you cultivate microalgae in a photobioreactor, you don't get maximum, beyond 1.2 to 1.3 grams per liter of water. And if you're doing this in a raceway pond, it's usually around 0.35 grams per liter of microalgae. So that means there's a lot of water in there that needs to be taken care of, and this leads to over 80% of production cost going into dealing with the water. And to that effect, there's also the problem of complex cell structure as well as small cell diameters. And to this end, a report or a paper written in 2011 actually shows that the cost of producing a gallon of biofuel from algae is between $10 to $13 a gallon. And there's another report that actually says that if you are to do the cultivation using photobioreactor, it goes as high as $20 a gallon. Now, comparing that with what we have here from this table, you can see that algal biofuel is still way, way, way more expensive. And so how do we break the barriers? Basically, people are looking at two major items. The first one is using low energy methods such as waste heat and sunlight. The other approach is the complete avoidance of drying, which is what our work is related to. But looking at the first approach, as it were, even if you have to use waste heat or sunlight, you still have to use some energy consuming processes to reduce the water to some. You can't just take a whole 1.3 grams per liter of algae and just keep it in the sun and expect the water to dry off. So, and when you're using waste heat, you're also required to install, some extra equipment, heat exchangers, pipes, and all that. So looking at the other alternatives that we've talked about, we selected the use of surfactants. And this is how we are working with our surfactant. We have a choice of surfactant, which is CTAB. It's cationic in nature, as you can see, the ammonium group there. Oops. How does this work? Anyway, the ammonium group is positively charged, and you can see that the algae has negatively charged functional groups. So that gives room for not just attachment, but also cell disruption through hydrolysis. So we, take advantage of these two features by putting our CTAB into work in our foam column. And this is how the foam column works. What you see on top of the mixer is like our feed tank. So to ensure regular mixing. So there's a connector from the feed tank to the column, and at the bottom of the column, there's a hose that actually supplies air, just bubbles air in there, and it generates foam. And once the foams are generated, they rise up the column, and as they go up, they do so with the algae along. And if you look at the second photo, you see that just below, it's practically white, and above it, it's green, which shows that you're having a separation of algae from water. And at the top, you get where you have there. So, but like I said, we're not just looking at solid liquid separation, we're looking at cell destruction as well. And I mean, reports have shown that CTAB particularly and other surfactants have the capacity to disrupt cell walls. So we are expecting that what we have at the top of the column are disrupted microalgae. But again, to achieve the third objective, which is oil extraction, we decided to put methanol into the mix. But for us to do that, we needed to investigate the effect of methanol in the whole setup. So we tested for surface tension. Looking at different ratios of water to methanol at different concentrations of CTAB. So we tried lower concentrations as well as higher concentrations. So as you can see, the higher concentration CTAB actually showed greater impact in terms of surface tension reduction. But in all of both cases, in both cases, you see that the trend it's almost the same. Once you have methanol in the system, it reduces the surface activity of the surfactant. So in other words, methanol controls the system. So in order to see how this works, in a real situation dealing with what we have, we tested different scenarios in our column. A is actually a representative of a scenario where we were generating the foams and we were actually supplying methanol from the top of the column, all right? And the other scenario was mixing, the culture with methanol, then adding surfactant. While a third scenario was where we mixed the culture with surfactant for a while before the addition of methanol. And as you can see, in the third scenario, at 30 milligrams per liter of CTAB, we were able to get solid separation, and hopefully, because the product that we collected has not yet been tested. But looking at it under the microscope, we could see that they were disrupted, and it shows some oily stuff. But we needed to test that using a GCMS, which for now is broken in my school, but they're looking at repairing that. So, and for the other case where we mixed the culture with methanol before the addition of surfactant, we needed as high as 70 milligrams per liter of CTAB. And for the other case where we were actually, sending in methanol from the top, it goes as high as 200 milligrams per liter. The essence of this is to make sure that we are using a process that requires as less CTAB as possible, because we don't want too much of the CTAB ending up in the product that we are intending to eventually convert to biodiesel, because we'd have to deal with cleaning that up as well. So that's basically the idea. And in conclusion, I try to compare our method with one of the other processes that's been tried in order to avoid drying, which is the use of nanoclay. And basically, this is a simple cost analysis, and out there it shows that compared to $0.05 for the CTAB, you require about a total of $3.6 for the nanoclay. And in the process of the nanoclay, there's also centrifugation involved, which is extra energy as compared to what we're doing here. So, and in general, we concluded that methanol has effect on the surface activity of CTAB, and once it goes beyond 50%, there's basically no effect, no visible effect in terms of surface tension reduction by the surfactant. Then allowing for better mixing of the culture with surfactant initially, reduces the surfactant dosage, which is good. I mean, like I said, we are interested in minimizing as much, as possible the CTAP that goes into our, final, starting material for biodiesel conversion. And in comparison, like I said, with the nanoclay process, this process looks more promising, and I think it has better process safety in terms of the chemicals that are involved. That's all. Thank you very much for listening.
Paper is open for questions. Could you tell me, the reason you added the methanol was to help extract the oil once the CTAB opens the cells? And are you running at an amount of methanol or a ratio of methanol that is comparable to what the methanol to triglyceride ratio might be when you transesterify?
Yeah, exactly, because like I said, these are preliminary results. So we just wanted to take the methanol as high as possible, but of course, the next stage is to use, if it works at 50-50, which is way, way above the ratio of methanol to oil that people are using currently. So we have a very good confidence that at lower methanol concentration, it's going to even work better.
Very good.
Yeah.
Further questions? All right, thank you.
Thank you.
I'm sorry, a winner has not yet been chosen, correct? As in other sessions, this is an Amazon Smile $50 gift card. If you would log on to NBB Connect, you'll be eligible for a drawing at the end of this next talk. Our final speaker is Mr. Chen Lee. Who was born in Taiwan, spent 5 years as a child in Madison, Wisconsin, as his father pursued further training there in forestry, and subsequently returned to Taiwan, where he received a bachelor's degree in agronomy at the National Chung Sing University in Taiwan, and returned then to the United States, where he received a master's degree in plant, soil, and agricultural systems from Southern Illinois University in Carbondale. He's currently a PhD candidate, expecting his doctorate in 2020 in agricultural sciences, again at Southern Illinois University in Carbondale. He has worked as an assistant technician in Nicaragua, funded by the Taiwan International Cooperation and Development Fund, and he has also served as a field representative for Bayer Crop Sciences. His research interests include soybean diseases quantitative trait loci mapping, particularly soybean sudden death syndrome, leaf blight, and reniform nematode infections. His long-term objective is an R&D career with a seed or biotechnology company. Chen?
Thank you for the introduction. I actually just arrived from Taiwan, so I flew for 14 hours to get here, but on record, I'm from Carbondale. So today I'm gonna finish my presentation with soybean quantitative trait loci mapping, and I'm gonna talk about the genotypic and phenotypic variants in soybean oil. This project was first proposed roughly around 2009, and we never got to submit it. So recently it was brought to our attention again, and we collected the phenotypic data, and now we are finishing up the project, and hopefully we can submit it somewhere after revision. So this project was done by myself, one of my first undergraduate student worker, John Lint, and my advisor, Dr. David A. Lightfoot. So I believe most people are fairly familiar with the soybean composition. So this is a really light introduction part. As you can see, soybean consists of mostly carbohydrate, protein, and oil. which means that soybean is really useful for like human consumption. In East Asia, we eat tofu, which is also known as bean curd, and soy sauce, which is a sauce often used in Chinese food. And for example, soy milk, it's also often consumed in the breakfast and vegetarian meat. Of course, soybean could also be used for livestock feed, and of course, today we are going to talk about biodiesel. So to continue on the introduction, we are going to talk a little bit about the soybean oil, which consists of 5 different fatty acids: stearic, palmitic, oleic, linoleic, and linolenic. So this sums up the basic information of these 5 fatty acids. As you can see, the melting temperature for stearic and palmitic acid is a lot higher. It's roughly 60 to 70 Celsius, which is 140 Fahrenheit. So in room temperature, they would be solid state, which on the contrary, the ones on the bottom, they would be liquid state. So the one that is written red right here is the one I am going to focus today about. So this one is the one that we do not want in biodiesel because of the solid state which gels. So to look at the structure, the C and D, the C to D, the carbon to the double bond, we could see that the stearic and palmitic acid is a saturated fat, whereas the other 3 are unsaturated fat. So as I mentioned previously on the previous slide, palmitic acid is not desirable for biodiesel. So this is straight out of a textbook. I'm just gonna mention the final one. And the one we are going to talk about today is the Cas1 gene, which this gene was found throughout different oil crops, like this was found throughout different crops, for example, like tobacco, Arabidopsis, to increase oil content. And what this gene does is it catalyzes the elongation of the acyl chain from 6 to 16. So previous report has stated that this gene would increase the total oil content of the crop. So this gene was reported to be on chromosome 5 in soybean, but it was never really mapped out. This database is Soy Knowledge Base, which is a project done by University of Missouri, and it's one of the soybean database for breeders. As you can see, this is an oil quantitative trait loci, which is a region of interest that corresponds with a phenotype. And the markers we are interested in is the SAT200 and SAT236. So as we mentioned, this gene quantitative trait loci is on chromosome 5, and we want to know the precise location and the function of it on soybean. So as I mentioned, the objective of this study is to know the relationship between the Cas1 gene allele and the oil productive and quality of the soybean through gene mapping techniques. So we are going to talk a little bit basic genetics over here, the mapping techniques. To start off with a mapping population, we would have to map out, we have to cross 2 different parents. One is the Williams 82, which was released roughly around 1981. And this was released for phytophthora rot, and this is used as the soybean genome reference. This was released by USDA ARS and also the Illinois Extension Station. The SX is released in 1973 by Virginia Experimental Station, and it was released for seed yield and seed quality. So we have to create something called a near isogenic line, which means they only differ in one quantitative trait loci. So after creating the near isogenic lines, we have to collect the phenotypic data, which was done by this Celtex 50 portable grain analyzer, and we collected the water, oil, and protein content. The data was additionally sent to Monsanto, done by one of our alumni, Melody, and we collected the 5 fatty acid content. So one important slide I am missing over here is the genotypic analysis. What we do is we plant the 17 different isogenic lines and we collect the leaf samples, extract the DNA, and we run the analysis. We run the PCR product on the agarose gel, and then we score them. Based on the score, we can tell what category they are from. Are they from the Williams 82 or are they from the SX? So after we have all these data, we combine them together. So the allele part is done by the genotypic analysis, and the phenotypic analysis is the oil and the palmitic acid. So as we could see, the average of the X6 is slightly higher than the Williams 82. If we run a statistic t-test, we could see that the p-value is smaller than 0.05, which means it's significant. So on the contrary, the palmitic acid, the SX is lower, which is desirable for our research for biodiesel, and the Williams 82 is slightly higher. So this is one of the figures we collected, the data, and as we could see, the palmitic acid, SX would be slightly lower, whereas the Williams 82 would be slightly higher. So this result would match the hypothesis that Cas1 gene allele affects the production of the total oil content and the palmitic acid. So we are trying to do further studies on this Cas1 gene, and we are going to send them off for further analysis. Hopefully we could get down to the candidate gene and know where the protein is and know the function. And this is my presentation. I would like to thank my student worker, John Lind, my colleague, James Anderson, to making this possible, and my advisor, Dr. David A. Lightfoot. This is the reference, and are there any questions?
Questions?
Thank you.
If I could ask you, is a QTL a single gene or a single protein product, or is it a large region of multiple genetic elements?
It's a large region of genes, and they are clustered in one region. There are a lot of genes within that quantitative trait loci.
Has anybody ever isolated a whole loci and measured how many base pairs it is or anything like that?
It varies on soybean. Like for the SDS I've done, we got down to the candidate gene, and we got down to like roughly 6. So there are like more than 10 or 20 clustered in one region. It depends on the loci itself.
Are there other loci that affect palmitate, so that if I wanted to drive it lower, I could try to cross those into this construct?
This is the first one I've done research on, so I am not sure, and I believe there are. And majority of the research done on this are done on like tobacco and other crops. So interesting thing about this is soybean, there is not a lot of publication.
Very good. Thank you, Yiche.
Thank you.
That concludes our session. Have we drawn the winner yet?
That was like really dry.
Amazingly, there's no conflict of interest clause, and Stanley Anderson is the #1 name. Thank you for coming today to support our students. Have a good rest of the conference.